to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
It's one small step for man, one giant leap for mankind.
On the 16th of July, 1969, the Apollo 11 rocket launched, headed towards the moon. But this wouldn't have been possible without some maths, and guess what? More maths. Without months of calculations and simulations, the launch would have been impossible. The trajectory, efficiency, amount of fuel required, and the force needed to launch was finally measured and recorded. Another example of the importance of maths is right above your heads right now. The International Space Station, or the ISS, is currently orbiting the Earth at 27,580 kilometers an hour, recording and examining our world. The International Space Station stays near our planet and doesn't just fly away because of the gravity pulling us together. But gravity is a constant force, so you may wonder, why doesn't the International Space Station just fall to the planet? Well, that's because of a thing called an orbit. When you throw an object forward on a planetary mass with gravity, the object, in this case a ball, is thrown forwards, but because of gravity, this object's trajectory will curve down as a result of gravity, pulling the object closer to the ground. But surely there has to be a way around this, you may think, and you would be right to think that, because otherwise you wouldn't be able to orbit a planet. This is the speed that you go at to overcome gravity and, at the same time, not fully escape it, to form a circular orbit. Just because you think you now have made an orbit that will last, think again. This is because of many forces that can act upon such satellite, but for most satellites orbiting around our planet, the main force is atmospheric drag, as our atmosphere, even at the heights of the satellites that orbit at low Earth orbit, there is some density of the atmosphere, leading to drag, which lowers the orbit even more until it falls to Earth, like what happened to the Skylab in the 1980s. The International Space Station counteracts this by using the boosters that it has and by using the force of resupply vessels to push the International Space Station higher.
Rockets create force by accelerating mass out the back of an engine. This is usually done by combining fuels and oxidizers, for example, hydrogen and oxygen. However, some situations call for unusual methods. One such method is ion propulsion. This involves using a statically charged grid to accelerate charged ions of gas and expel them at very high speeds, making these engines very weak but incredibly efficient. This works because of Newton's second law of motion. Net force is equivalent to mass times acceleration. Therefore, if you fired a 1 kilogram cannonball at 100 meters per second, you would need 100 newtons of force. But what is a newton? A newton is typically defined as 1 kilogram times meters per second squared.
But how do we use all of this technology on an everyday basis? Do you enjoy knowing what weather it will be while also being quite accurate? Well, satellites help with this too. By having a larger perspective of the planet, meteorologists, people who study and practice meteorology, can more precisely monitor the current weather and predict the next day's weather, while also keeping the accuracy quite high. Whenever you use the mapping service to give you directions, you are using the Global Positioning Service, GPS for short, and all kinds of digital communications between data centers and satellites. Without the use of astronomy, this service just wouldn't work. If you ever use the internet on an aircraft, well, this too wouldn't be possible without the use of satellite communications services. This is because the Wi-Fi on an aircraft is, unlike how Wi-Fi is usually, going from the ground to a satellite, then to the plane. All of these things and so many more wouldn't be possible.